Hi, welcome to Algebra 2 Common Core. In today's lesson, we're going to work on solving square root equations. So please fill in the steps in your note packet on page 5. In step number 1, let's isolate the radical on one side of the equation. So do whatever you need to do, whether you're adding, subtracting, multiplying, or dividing, to move terms other than the square root to the other side of the equation. Step number 2, once the radical is by itself on one side, we're going to square both sides of the equation to eliminate the radical. In step number 3, once you've eliminated the radical, then we have an equation that's easy to solve. So let's solve for that variable. We might have a linear equation, we might have a quadratic equation, so we'll follow the steps necessary to solve for whatever kind of equation I'm left with. My last step is my most important step of all. Once we get our solutions, we have to check those solutions in the original equation. Make sure you're always going back to the original equation, because sometimes when we do these steps for solving a square root equation, we introduce what's called extraneous roots. So we want to make sure that our solutions are actually solutions for the original equation. In exercise number 1, we have a group of equations that are all involving square roots. So we want to solve these square root equations and then make sure that we check each solution. Part A is a very easy square root equation. We see that we've got the square root of x is equal to 7. So since the radical is already by itself on one side of the equation, we want to square both sides of the equation. Now, because squaring and square rooting are inverse operations, when we square a square root, that gives us just what's underneath the radical, called the radicand. In this case, we have x. So our answer, x equals 7 squared, which is 49. Now we need to go back and be sure that we check this solution in our original equation. So when we do that, let's substitute the 49 for x. So we have the square root of 49, which is in fact equal to 7. So we see that yes, this does check in our original equation, and my only solution is x equals 49. Let's try b. When I look at this, I see that the radical is already by itself, so I'm going to square both sides of my equation. That gives me x minus 3 when I square the square root, and on the right side, 5 squared gives me 25. Let's get the x by itself, so we're going to add 3 to both sides of the equation. So we have x is equal to 28. Go back and check in the original equation. So the square root of 28 minus 3, does that equal 5? Of course, the square root of 28 minus 3 is 25, and the square root of 25 is 5, so that does check in the original, and my solution for this radical equation is x equals 28. Sometimes you'll hear me talk about it as a radical equation. Other times we call it a square root equation. A radical can be any root, but a square root specifically has a root index of 2. Let's go to part C. So in part C, I'm going to square both sides of my equation. Squaring the square root of 2x minus 1 gives me 2x minus 1. Don't forget to square the 4 on the right side, so that's equal to 16. Adding 1 to both sides of the equation, I now want to solve this equation. This is just a linear equation, as was the last one. So that tells me that I'm going to get one solution for x. So dividing both sides by 2, my solution is 17 halves. But to go back and check, I'm going to say the square root of 2 times 17 halves minus 1, does that equal 4? So 2 times 17 halves is giving me 17. 17 minus 1 is 16. So this is the square root of 16, which is 4. So that checks in the original, And my equation answer, x equals 17/2. As we progress through these examples, we see that the examples are getting a little bit more complicated. In part D, I've got 3 radical x minus 4 equals 20. So this does involve some work in getting the radical by itself. I'm going to add 4 to both sides of the equation. So that's giving me, 3 square root of x is equal to 24. Now let's go ahead and divide both sides of the equation by 3. So I now have the square root of x is equal to 8. So this looks just like the first example that we had. Now we're ready to square both sides of the equation only because I got the radical by itself. So squaring the square root gives me just an x. 8 squared is 64. So this is the solution that I want to go back and check in the original equation. So 3 times the square root of 64 minus 4, does that equal 20? Square root of 64 is 8. 3 times 8 is 24. So 24 minus 4 does equal 20. So that checks. So my solution for this square root equation is x equals 64. And as you can see, I was still getting a linear equation that I'm solving, so I have one solution. But I do need to check that one solution because occasionally there will be solutions that don't check in the original. So, trying part E, let's subtract 7 from both sides of our equation so that I can begin to isolate the radical on one side of the equation. Let's divide both sides by 2 so that I have the square root by itself. So the square root of x plus 5 is equal to 3. Now we're ready to square both sides of the equation because the radical is on one side by itself. So squaring the square root of x plus 5, I get x plus 5 equals 3 squared, which is 9. When I subtract 5 from both sides of the equation, it looks like my solution is x equals 4. Now let's go back to the original equation. 2 times the square root of 4 plus 5 plus 7, does that equal 13? That's a question mark there. So 2 times the square root of 9 plus 7, does that equal 13? 2 times 3 is 6. 6 plus 7 does equal 13. So that answer of x equals 4 is the only solution for my square root equation. For f, I want to first of all get the radical by itself. Let's add 4 to both sides of the equation. So now I've got a 40 on the right. Dividing both sides by 5, I have the square root of 3x minus 2 is equal to 8. This is where we're going to square both sides of the equation. So I've got 3x minus 2 is equal to 64. Now I'm ready to solve for x, and again it's a linear equation because it's got an x to the first power. So if 3x is equal to 66, x would be equal to 22. And again, it's necessary to go back and check. So 5 times the square root of 3 times 22 minus 2, subtract 4, does that equal 36? So 5 times the square root of 64, which is of course 8, minus 4 does equal 36. So that checks, and my solution is x equals 22. Now, don't be thrown off by example number 2, where we have a radical, but the radical involves a fraction. I'm going to solve this by again getting the radical by itself on one side of the equation, so I'm going to divide both sides of the equation by 3. So I now have the square root of x over 2 is equal to 5. Let's square both sides of the equation. So that makes my left side nice and easy. X over 2 is equal to 25. When I multiply both sides of the equation by 2, I get x is equal to 50. Now that looks like our solution, but we need to go back and check in the original. So 3 times the square root of 50 divided by 2, does that equal 15? 3 times the square root of 25, square root of 25 is 5. 5 times 3 does equal 15. So my solution is x equals 50, and I'm going to choose choice number 3. Exercise 3 introduces us to slightly more difficult radical equation. It's not harder in that I'm going to square both sides of the equation first. So that now gives me 56 minus x is equal to x squared. But what I should notice here is that I no longer have a linear equation. This is now a quadratic equation. Quadratic because I've got an x squared as the biggest exponent. So I'm going to want to write this in standard form. Let's add x over to the right side of the equation and subtract 56 and set the entire equation equal to 0. Now this is where we've got some options for solving quadratic equations. Our easiest option is to do factoring. Because I've got a 1 in front of the x squared, I can go directly to my parentheses and say, let's look for two factors that add to give me 1x, but when I multiply, I get negative 56. So this, of course, is going to be x plus 8 times x minus 7. Make our t-bar, set each factor equal to 0. So one solution should be x equals negative 8. The other solution should be x equals 7. Now we see that we have a variety of combinations of those answers in our choices. So of course what we're going to need to do is check both solutions. So take a few minutes and check both solutions and then come back and see if your checks agree with mine. Let's check our solutions. So when I checked x equals negative 8, I substituted negative 8 into the original equation for x. So on the left side, I get the square root of 64, which is, of course, positive 8. Remember that square root means take the principal square root or the positive square root. On the right side of the equation, I substituted negative 8 for x. So really what I have here is 8 equals negative 8. Which of course is not true. So that's why we are going to say our solution of negative 8 does not work in the original. We're going to reject that answer. It's called an extraneous solution. So an extraneous solution is a solution that looks like it's going to work, but when we go back and check in the original, it doesn't. Let's try x equals 7. Again, going back to the original equation that has a square root in it. The square root of 56 minus 7 is the square root of 49, but the square root of 49 does equal 7, so that check works. So we're going to keep the solution x equals 7, but we're going to reject the solution x equals negative 8. So this next paragraph talks about what we just found out. Oftentimes, roots are introduced by various algebraic techniques. In this case, when we square both sides of the equation, that for one reason or another are not valid solutions of the original equation. These roots are known as extraneous roots. If you've got your highlighter, please highlight that in your notes. And can always be found by checking with the original equation. So when roots don't work in the original equation, we're going to reject those roots. Now let's try a couple more complicated examples in exercise 4. Part A says the square root of 2x minus 3 is equal to x minus 3. The radical is by itself, so that tells me go ahead and square both sides of the equation. Now be really careful on the right side because I've actually got two terms. So when I see that, I've got to square the whole binomial. I can't square each one individually. It won't give me the same solution. So on the left side of the equation, I've just got 2x minus 3. On the right side of the equation, I'm going to square x minus 3. So I'm going to multiply the binomial x minus 3 times itself. The left side just stays 2x minus 3. On the right side, you can either do double distribution to multiply those binomials, or you can use our pattern where we say square the first term, x squared, multiply the product of the two pieces by 2, so that's going to give us negative 6x, and then square the last term, so that's going to be a plus 9. Now let's go ahead and subtract 2x from both sides of the equation. And let's also add 3 to both sides of the equation, because we want to write this equation in standard form. So I now have x squared minus 8x plus 12, and there's nothing left on the other side, so I'll say equals 0. Do you notice that this equation is once again a quadratic equation? So if it's quadratic, we can't just solve like we do linear equations. We're going to have to look at this and say, is it factorable? And in this case, yes, it's a nice, easy factoring. So we're going to say x and x. I want to add to get negative 8, multiply to get 12. Those two numbers would be negative 6 and negative 2. Set those factors equal to 0. Make your t-bar, and I get x equals 6 and x equals 2. Now we can't just assume that both of those work in the original equation, so let's go back and do a check for each of them. So for x equals 6, I've got the square root of 2 times 6 minus 3. Does that equal 6 minus 3? So I have the square root of 12 minus 3, which of course is the square root of 9. And yes, that does equal 3. So that tells me let's keep that solution of x equals 6. Now, there's nothing saying that both solutions can't work. Sometimes both will work, but we have to do the check to make sure. So if I've got x equals 2, let's substitute 2 into my original equation. So 2 times 2 minus 3, does that equal 2 minus 3? So this is the square root of 4 minus 3, which is just the square root of 1, which is a positive 1. However, on the right side of the equation, 2 minus 3 gives me a negative 1, and I can clearly see that 1 does not equal negative 1. So I'm going to reject the answer x equals 2 because it didn't work in the original. It looks like it's going to work, but when I go back and check it in the original, it doesn't solve that original equation. Now, for part B, we're going to have to do one additional step before we square both sides. I want to get the radical by itself, so let's add 2 to both sides of the equation. So I have 2x plus 2 is equal to the square root of x plus 6. So let's square the radical side, but on the left side I've got a whole binomial, so let's remember to square the whole thing. Show that by putting that binomial in parentheses. Now when I square 2x plus 2, I've got to square the first term. So 2x squared gives me 4x squared. I want to take twice the product of the two terms. So 2 times 2x is 4x. Double that, and it gives me an 8x. And then square the last term, so I now have plus 4. On the right side of the equation, I'm squaring my square root, so that just gives me x plus 6. Again, I see that I have a quadratic equation, so I need to follow the steps for solving a quadratic equation. I'm going to put it in standard form by subtracting x from both sides of the equation and also subtracting 6. So I now have 4x squared plus 7x minus 2 equals 0. Now there's no GCF in this quadratic equation, so that tells me that I've got to do some factoring because I've got a number in front of the x squared. I can either do grouping or I can do my box method. I love the box, so let's do that. 4x squared goes here, negative 2 goes here. I have to find two numbers that multiply to give me negative 8. And when I add them, I have to get positive 7. So if I think about this, I think positive 8x and negative, oh, wait a minute, I think that's a negative, nope, positive 8x and negative 1x are my combination that work. In the first row, 4x is common to both. In the second row, negative 1. In the first column, x, and the second column, 2. So it's looking like my factors are going to be x plus 2 times 4x minus 1. When I make the t-bar, I get x equals negative 2, or x is equal to 1/4. But both of these answers need checking before I can see that they are solutions to the original. Go ahead and check these solutions in the original and see if you think they are both solutions for that equation. Come back and check with my check and see if we agree. Welcome back. In your checks, did you see that x equals negative 2 does not work in the original? So I'm going to reject that answer. But when I checked with x equals 1/4, I did get that the sides match, so therefore x equals 1/4 is a solution of that radical equation. In example number 5, we're going to take a look at both a graphic and an algebraic solution for a radical equation. So I'm given two equations, y equals the square root of x plus 3 and y equals x plus 1. We know how to graph y equals the square root of x plus 3. Let's think back to our transformation unit. And we know that this means that I've got a shift of 3 units to the left of my regular parent function y equals the square root of x. So I can picture what this graph is going to look like. I'm going to take a few minutes to make a table of values, focusing specifically on numbers that give me perfect squares underneath the radicals, so it's easier to graph these. So for example, negative 3 is going to be my first value for x. The square root of negative 3 plus 3 is going to give me a 0. When I try the next value, how about negative 2? The square root of negative 2 plus 3 is just 1. I don't want to use negative 1 because that's going to give me the square root of 2, which is irrational. Same thing with 0 because that gives me the square root of 3, which is irrational. So instead I'm going to jump to an x value of 1. Square root of 4 is equal to 2. And let's go with 6 for x, so the square root of 6 plus 3 would be the square root of 9, which is 3. The second equation that I want to graph is a linear equation. So do me a favor and take out maybe 2 different color pens and graph both equations on this grid and then come back and check. So pause the video while you do your graphing and then come back and check with mine. I've shown both of my functions. The black graph represents y equals the square root of x plus 3. And clearly you can see that we've taken our regular parent function of the square root of x and we have shifted it 3 units to the left. The beginning point for this graph is negative 3, 0, and I don't have any values to the left of negative 3 because those would give me negative numbers underneath the radical. For the blue graph, I graphed my linear function y equals x plus 1. That had a y-intercept of 1 and a slope of 1. So I've graphed this blue equation y equals x plus 1. Now when I'm solving this, I see that I have one point of intersection on my graph. So that point of intersection is the point 1, positive 2. Now let's take a look at the algebraic solution for this system. So you'll notice that I have two equations. That's what makes it a system. Because both equations is set equal to y, I can use the method of substitution. So I'm going to substitute one y for the other and get the equation square root of x plus 3 is equal to x plus 1. In essence, I'm just setting the two equations equal to each other because they're both equal to y. Now this is all set up with the radical by itself, so like on our previous notes, I'm going to square both sides of my equation. On the left side, squaring the square root just gives me x plus 3. On the right side, we're going to square this binomial, so square the first term, x squared. Take twice the product of the two terms, so plus 2x, and then square the last term. This is a quadratic equation, so I'm going to solve the quadratic. Let's subtract x and subtract 3 from both sides of the equation. So I now have 0 equals x squared plus x minus 2. This is a nice, easy quadratic to factor. So x and x add to give me 1, multiply to give me negative 2. So let's see here. I think my factors are going to be x plus 2 times x minus 1 equals 0. Make your t-bar, and I see two solutions, x equals negative 2 and x equals 1. Now I can clearly see that in part A, I only had one point of intersection, so that's helpful to look at the graph and say, how many solutions am I going to end up with? Notice that in part A, this second coordinate is really the y-coordinate. It's not a second solution. My only solution is 1. Now that's going to become evident when I go ahead and check my answers. So for my checks, I'm going to go back to the original. Let's start with x equals negative 2. I'm substituting negative 2 into x in this equation right here. So I'm going to say the square root of negative 2 plus 3. Does that equal negative 2 plus 1? That's going to be the square root of 1 equals negative 1, and that is not true. So I'm going to say no, so that's why we're going to reject this answer of negative 2. We could see that on the graph as well. Let's now check x equals 1. When I check that, I'm going to have the square root of 1 plus 3. Does that equal 1 plus 1? So the square root of 4 does equal 2. That checks, and the solution that we're keeping is x equals 1. So to finish this example, question C says, why does your answer from part A contradict what you found in part B? Well, in part A, I only had one point of intersection. But then when I solved algebraically, it looked like there was going to be 2 points of intersection. So clearly this is a contradiction. There are not 2 points of intersection. So what that tells us is that only one of the solutions will work. So we have to do our checks to determine which solution is actually a solution of the original. So again, since we can clearly see this on our graphing calculator can help us to at least decide how many solutions there's going to be. In this case, there was only one point of intersection, so I should know to expect just one solution. We've done a great job today with solving radical equations. We'll be working some more with this in class. So please make sure that you come and ask any questions that you have and be prepared to solve radical equations in class. Have a great night. See you next time.